We will not always be given the functions. We can just use the rules we have learned before. Sometimes we will be given the multiplication or the quotient form of the functions for the real-world application. That's why we need to use a different type of rules. If you remember the rules we have learned in the previous section, they don't include such a rule. We just learned how to take the derivative of the sum of the two functions or the difference of the two functions. But let's say, okay, you wanna take the derivative of this type of functions, f times g prime. So of course we can prove, okay, how we obtain the formula on the right hand side, but we are gonna skip for the sake of the easiness for this class. But the idea behind, okay, how we get this rule is to use the limit definition of the derivative, guys. If you use the limit definition of the derivative of the multiplication will exactly be on the right hand side. As you see, you can just repeat that formula in this way. The derivative of the second function, this is the second function, and then multiplied by the first function, and then the derivative of the first function, and then multiplied by the first function. So you are going to keep the other one same without taking the derivative, and then you need to multiply the other function derivative, and then you need to add them when you apply the product rule. So let's see in an example. Example will include the derivative. So we can use a different name, h of x. Here 2x plus 5 times x to the 4 plus 3x squared. As you see, I have two functions multiplied. This is my first function, okay? This is my second function, as you see. The rule says, what I should do when I have two different functions. What I should do first, I need to take the derivative of the second function, which is x to the 4 3x squared derivative, and then I need to keep the first function same, and then plus this time I'm gonna take the derivative of the first function, and then I'm gonna keep the second one same in this case. So if you look at here, it is exactly what the rule says: f g prime plus g, or we can say f prime times g, right? And then on the left hand side I have my function, the derivative. So let me apply the other rules we have learned to take the derivative of this multiplication. Since the derivative of the g prime will require you to use the other rules. So I'm gonna keep the first one same, 2x plus 5, and then the derivative of the second one is equal 4x cubed plus 6x using the power rule. That's it, right? The derivative of the 2x plus y is just 2, and then I'm just going to keep this part the same. So that's it. I'm going to leave here in this way, since you don't need to require for this for the derivative purpose, you don't need to require to simplify this process. But of course, if you want to do that, you can do it anyway. Maybe one more example. H of x is equal square root x plus 5 times x squared minus 3. Okay? The question is same, h prime x. I'm going to take the derivative of the second function and then multiply by the first one, and then I will do the other way around. The derivative times x squared minus 3. So I kept the second one same in this case. The derivative of the square root, just use the power rule again, the power rule. It is going to be equal 1 over 2 square root x. The derivative of 5, which is equal just the 0, since it is a constant. And sorry, here we should take the derivative of x squared minus 3, right? My bad. So I'm going to keep this same. It doesn't change, since we will do the same thing on the second side. So it is going to be equal to 2x, and then the derivative of this part is going to be equal 1 over 2 square root x. The derivative of 5, which is equal 0, and then x squared minus 3. So as I said, okay, you can just go ahead and then simplify as much as you need for the rest of the question. We can obtain the quotient rule in the similar way. You need to use the limit definition of the derivative to obtain the quotient derivative rules, guys. We're not gonna show how we obtain, okay, here. As you see, the top part of the formula, okay, will be similar to the product rule. It is just a difference, right, with the minus, as you see here, right? The top part is almost same, except the sign here. You should put the negative instead of the positive. But on the bottom part, right, you should take the square of the second function in your equation. So the second function is the bottom function, and then you need to take the square of it and then put it back to the bottom part. Okay, that's the formula. Now we can see a couple of examples how we can apply the formula. Example, h of x is equal x squared plus 5 over, right, the x plus 3. Okay, so if I would like to take the derivative of it, the formula says, so I'm just going to apply the product rule with except the sign between the terms, right, which is going to be equal then 2x times the second function minus this time, right? I'm just going to take the derivative of the bottom part, which is, as you see, 1 times the first function, which is going to be same. And then also what you need to do, you need to take the square of the, right, the bottom part. So here I can go ahead and I can simplify it. I don't wanna leave in that way. 2x squared plus 6x minus x squared minus 5 over x plus 3 squared. And then the top part is gonna be equal x squared plus 6x minus 5 and then x plus 3 squared. Okay, that's how we apply the quotient rule. Let's look at this example. This is the function, okay? You can find out how many facts you can remember after specific hours later. And psychologists model, right, this case by this function, just collecting some information and applying some statistical techniques, okay, to get this formula. And then here we are asked, okay, what is the rate of remembering, right, after such an hour. So as you see, this is the quotient type of functions, right? You have the rational expression. That's why you need to figure out the derivative of the quotient, applying the quotient rule. If you apply that, what you should do, you should take, right, the derivative of the first function here, and then keep the second one same. Look at the bottom part. And then you should do the same thing, right, the other way around. The second function on the bottom, and then you should keep the first function same. So this is the derivative of the second function, and then you should take the square of the bottom part. If you do some arrangement here, okay, you will get, right, this function as a derivative of this remembering function. So let's calculate, right, how many facts you could remember, right, after 1 hour. What is the rate of remembering, right, those facts? So you are just gonna use, right, basically x equal 1 or the t is equal 1 in this rate of change function, which is the derivative function. So this is the 100th facts, right? It keeps decreasing, but as you see, after 10 hours, right, the rate of change of the facts remembering will be less as usual. So depending on the situation, of course, but we experience the same situation actually in real life. Of course, you can discuss the correctness of this model, but as you see, if you accept this model is correct, okay, that's how it works. Another example from finance. So we would like to calculate the revenue increasing rate. We just had some rate change about, right, the demand and then price, but we don't have their functions. But what we know, revenue is, right, the demand type price, right, the demand type price. So demand, you can, if you measure how much demand you have, you can just, right, to multiply that by the price you sell, right, you can find the revenue, of course. In this case, those are all these variables actually are functions. These all variables are the functions of time. So I can definitely look at the rate of revenue depending on time, demand times, right, the price depending on time. Okay, so what I am being asked here, right, the revenue change over time. As you see here, look at that. I can take this derivative using, right, the product rule for the derivatives. So I need to keep the demand function same and then multiply by the, right, the derivative of the price function. If you want to calculate the revenue change over time, here the time change rate over month. So look at, I need to know, okay, all these values. So do I know the, right, the demand change? I look at that. I'm given that, right? Look at that. The 30 quarts a month demand was going up. So I can put it back. Do I know what the price, how the price is changing? Look at that. $0.5, right, each month, price is increasing. So I can use that one. So I need what? I need some values for to look at that price and then demand function. I know that's right, the price was equal $15, right? I didn't change. And the demand was, right, for the $15, it was, right, the 500 quarts. So if you do this calculation, so revenue will change, right, the 700 quarts, right, per month, guys. So this is the way how you can calculate, right, your revenue change. And then this idea actually will give you a lot of insight about your revenue adjustments or your price adjustment, okay? That is how they use in real life.